I'm going to talk today about optimized off-site construction and how off-site manufacturing can bring or provide buildings with low carbon and high function. Right, so the built environment accounts for approximately 25% of global CO2 emissions. Reaching net zero by 2050 will require buildings and construction industry to decarbonize 3 times faster over the next 30 years versus the previous 30. Wow. This sounds almost like an impossible thing to do. I would say that I believe we can do it. It's certainly very challenging. And this tells us that we all need to take immediate actions and consideration in tackling the root causes for reduction of global carbon footprint. Reducing CO2 throughout the design, construction, and operation phases of our new buildings and infrastructure is the key. So we will ask, what actions can we take? And how can we contribute and collaborate to succeed? One of the steps is certainly off-site manufacturing, because OSM increases efficiency, saves time and energy, reduce pollution, reduce material waste, and ultimately leads to reduced carbon footprint. I will be moving briefly explaining what is embodied carbon in built environment and what crucial aspects of planning and designing we should take as engineers in realizing or exceeding net zero targets. While both operational and embodied carbon contributes to overall whole life carbon emissions, embodied carbon can be defined as the carbon output produced during the construction of a building. This includes the manufacture and extraction of materials used for buildings construction and transporting and installing those materials to the site. In recent years, there is a significant steps taken to reduce operational carbon with substantial improvements in technology and energy efficient appliances. In comparison, we are still using carbon-intensive methods of making our building materials and constructing our buildings. This is the reason why it is crucial that we address embodied carbon levels and work to reduce this within the built environment. Graphic on this slide, taken from the iStruct shows that the construction life cycle is split into 4 stages. Stages A1 to A5 relate to the product and construction phase and internal embodied carbon generation, while the modules in B stages relate to the building or structure's lifetime use. They are classified as operational carbon. Beyond the 4 life cycle stages, a separate section covers some miscellaneous carbon outputs that should be considered. They are called beyond the life and cover benefit or load for recycling materials, energy recovered from materials, and the reuse of materials. Off-site manufacturing and building information modeling, BIM, are the 2 techniques in increasing use in the recent years in engineering and construction industries and should be at the heart of our design proposed solutions. Building with prefabricated modules can bring time saving of 50 to 90% and also cut the whole life costs of assets. Construction industry can be extremely dangerous for its worker and potentially damaging to the environment. When sites are hot, dusty, windy, or constrained and busy, and critically in an environmentally sensitive location, the likelihood and accident can increase. Assembling micromodular parts into larger components in comfort-controlled environments ready for shipment to site, not only that protects human life and environment, it also increases the quality of the building across every aspect. To conclude, plug-in, plug-out modular section reduce the time and cost of adaptation, repair, maintenance, and carbon emissions associated with manufacturing while producing high-function buildings with enhanced social outcomes. But how we design for off-site manufacturing? When the design starts, designers should look at the initial briefing conceptual and procurement stages of a project or program, and identify issues related to designing for manufacturing, for logistics and assembly, including handover. They should also consider how OSM might impact on the whole life operation and maintenance of a built asset, even its disassembly and reuse. The design intent starts with maximizing raw materials. Some measures to reduce embodied carbon can include cement replacement admixtures in the specified concrete mixes such as GGBS or fly ash, higher strength concrete for concrete columns and vertical elements that ultimately reduce the total consumption, reduce column sizes and reinforcement quantity. Recycled materials should be used. Reinforcement bars manufactured from predominantly recycled material. Other sustainability measures can include building in flexibility. For potential change of use, this would actually minimize or even avoid structural alterations in future. Consideration of potential disassembly and reuse of structural elements, and example of that would be minimizing welding on site and with the preference of bolted connections. From the commencement of concept design, designers, and that includes architects and engineers, should focus on producing a unique set of buildings using a standard kit of parts where possible. Parametric design should be used to test the various options and to achieve the minimum number of different components necessary to develop, produce, and deliver the vision. Once concept has developed, designers should enter into an early agreement with the local OSM market and test around key criteria such as safety, quality, reliability, and continuity. Once a preferred shortlist is chosen, suppliers become an active part of the next design stages. This also means that market is prepared and familiar with the design intent and the project before they are formally asked to tender for the works. Ultimately, the buildings will be developed with as many system integrated as possible, with only final plug-ins required. Critical part of the early design process will be addressing the building's life cycle. Life cycle analysis report that will further detail the material selection and credits to be achieved should be developed and integrated at design development stage. Optimize energy use, regular, planned, and safe preventive maintenance, discrete access, periodic replacement, eventual deconstruction with health and safety consideration at the forefront should be fully analyzed with clear strategies established for each. The earlier the life cycle impact of material is assessed, the greater the chance to reduce the carbon and environmental impacts. The graph on this slide shows opportunities to reduce carbon following the project life cycle by embedding the carbon hierarchy in OSM construction. Okay, whether the buildings are delivered in a true modular form or as a separate components for a more intense site assembly, regularization and standardization of parts is critical. This happens in the factory. The OSM elements are then transported by roads or shipped, and ideally, chosen fabricator will have their facility near to the site, preferably with an easy access where assembly will take place. Components will be manufactured and dispatched in strict order to suit site phasing and assembly. Once they are finally delivered on site, the assembly will take place, locking prefabricated elements into in situ and permanent structures. In this slide, I wanted to highlight a few potential challenges related to OSM construction. And as designers, and while designing for the OSM, we all must consider the following parameters at least. Suitability depends on the architectural design intent, location, and local construction practices. OSM demands proper and more communication between on-site and off-site workers, and the fact that in Middle East, labor is cheap, materials are expensive. Customization in modular construction is limited in terms of the weight, transportation, and handling on site. And last but not least, lead-in time should be taken into account. This slide shows the benefits of OSM. And key benefits, from my point of view, include the following. Structural units are manufactured in the factories under controlled factory settings. Thus, offsite construction produces the final product with extreme quality. In offsite construction, the majority of the building elements are manufactured in the factory, hence the weather conditions do not affect the manufacture. The only site time and conditions affected are during the assembling. There is improved site logistics and better waste management, less material waste, better health and safety, lower whole life costs, lower whole life carbon, higher reuse of components, and shorter construction program that lead to reduction of construction traffic, on-site labor, and deliveries on site. I would like to end this presentation by encouraging all architects, engineers, contractors, and clients to develop or continue proposing OSM solution, because driving efficiency and quality in construction manufacturing resulting in a more resilient and effective infrastructure fit for future needs. And I'm sure that you will all agree with me that we want to contribute to better social outcomes, save our planet, and build a better world.
If I haven't heard it once, I've heard it several times, that in the Middle East, the business case to use offsite modeling, offsite construction is, there's no ROI because labor is cheap, materials are expensive. But I really challenge this, right? I look at the benefits that you've articulated in the last slide. There are tangible and intangible benefits. So have you done an ROI to really take into account both sets of benefits to see if offsite construction does really result in a sustainable ROI?
Yes. So in Mott MacDonald, we did a couple of projects when we proposed offsite manufacturing, and one of the projects is Red Sea Hotels on the Red Sea for Red Sea Development Company with Foster and Partners as architects. First of all, it depends all of what architects come up with as an architectural design intent and how that scheme is suitable for OSM construction, I would say. So it can be very expensive if you want to push towards OSM regardless of architectural intent, or it can be less expensive if you challenge your architects in modifying slightly the scheme to suit more OSM. So there is no one answer to your question or straight answer. OSM construction can be very expensive. It depends on the various things. I mentioned architectural design intent. I mentioned Middle East, where a fact is that materials are expensive and the labor work is cheap. However, for the future benefits, for sustainability that can OSM bring, I would always go with trying to find solutions that are equally economically efficient as well as design efficient with OSM.
Have you any case studies or information or percentages that you would put against how much embodied carbon can be reduced on a project by using offsite manufacturing?
This percentage or kg per cubic meters will depend on what the solution from offsite manufacturing you are proposing, whether that's a cement replacement admixture in your concrete, whether that's something else. But that, yeah, definitely whether that's concrete or steel or timber building, and whether that timber building is built in Europe or built in KSA. So yes, we do have all these comparison done for some of the projects in Mott MacDonald, yes.